Okay, we were discussing the p is an atomic orbital. If you remember, we made a plot of the radial part of the function, and we found that it starts at the origin and then increases, reaches a maximum and then decreases. This is the radial part. We also made a plot of the angular part, and for that we used what is referred to as the polar plot. And if you say that this is the YZ plane, then what happens is that the polar plot consists of two circles of the same size just touching each other at the origin. And I also argued that if you wanted to get the three dimensional appearance of this polar plot, what you should do is you should take this figure, rotate it about the z axis, and then you will realize that the two circles will describe surfaces of two spheres just like that touching each other at the origin. So, this is the angular dependence, that is the radial dependence. I can now combine both of them to get the actual three dimensional appearance, which I shall represent by shading. But before I forget, I also should tell you that in these directions the wave function was positive, while in this direction, in the downward directions, the wave function was actually negative. So, this is the radial part, which is actually R21, and this is actually Y10, if you want to know what the functions are. So, now how will I represent the function by shading? The answer is quite simple. If you say, okay, here is the nucleus, near the nucleus you will see that the radial part implies that the wave function has a small value. In fact, at the nucleus the value of the wave function is 0. But as you go away from the nucleus, what does it say? The wave function actually would increase, correct? But then you look at the angular part, you see, after all the wave function is a product of the radial and the angular part. So, the angular part has the maximum value in the either in the positive direction, it has the largest value either in the positive z direction or in the negative z direction. So, what will happen is that you will have let us say an appearance which I shall try to represent here. See, when I represent it by shading, I would not have any density of shading near the origin, but then when I go away from the origin, it is going to, the density of shading is going to increase, but the density will be actually the shading will be concentrated along either the positive z direction or along the negative z direction, that is implied by the angular dependence. And in the downward direction, what will happen? You will have again a similar kind of appearance, and if you want, I mean, one can, well, of course these are identical, though they do not appear to be so in what I have done, except for their signs they are identical. So, this is plus and that is minus. And not only that, if you think of any point on the y axis, you would realize that for that point the angle theta actually is 90 degrees, and remember the angular part of the function was actually cos theta. This contained y10 is proportional to cos theta. So, what will happen is that if you think of any point along the y axis, theta is 90 degrees, and therefore what will happen? Cosine of 90 degrees, which is actually equal to 0. So, anywhere on the y axis actually it is 0, but not only anywhere along the y axis, you think of any point in the xy plane, the value of theta is 90 degrees. Any point in the xy plane, if you remember polar coordinates, you would realize that for any point in the xy plane the value of theta is 90 degrees, and therefore any point on the xy plane you will have a value 0. just above the xy plane you will have a positive value, while just below the xy plane you will have a value which is negative. So, that is how the appearance is, and in fact I have a figure to show you this. So, this is the appearance of the plot just confined to the x, well here it is xz plane, it does not matter whether it is xz or yz. So, that is how the appearance is, and in fact if you look at this part you see it is going to be positive, and if you look at this part it is going to be negative. As you can see, the this actually is not just a density plot. In addition to the density, it also has plotted the contours along which the function has constant value. For example, if you look at this value, you see along this contour, everywhere along this contour the value of the function is 0.034. While along this contour, what will happen, the function has magnitude wise it has exactly the same value, but the sign is opposite. Okay. And also it is possible to make polar plots of such functions using this nice software called Mathematica, and I would demonstrate that also. What we are interested is in a polar plot of Pz, and you see this is how the polar plot, 3-dimensional appearance of the polar plot would be. Okay. Now, the advantage of this kind of software is that you can actually view it from any angle if you like. Okay. You can rotate it and view it. So, that the 3-dimensional appearance of the polar plot is clear. You see what I have described, it is just two spheres touching each other at the origin. That is what happens with P is an atomic orbital. Okay. And now we will look at the other P orbitals, as I have mentioned in the previous lecture. I am thinking of n is equal to 2, L is equal to 1, and then I said m is equal to 0. This gives me this particular atomic orbital, which we normally refer to as a pz atomic orbital. To be very precise, we put a 2pz because P2 is the principal quantum number. Then if n is equal to 2 and L is equal to 1, and m is equal to maybe plus 1 or minus 1. What is going to happen is I will have psi 2 1 plus or minus 1, I shall write them together. These are functions of r theta phi, and it is going to be equal to r21 of small r, because remember the way the wave function was, even if you have 3 quantum numbers n, L and m, r depends only upon 2 of them, and the angular part of the wave function again depends only upon 2 of them. So, this is how the function is. If you remember, this is something that we have already discussed. So, therefore, if you had y psi 2 1 plus or minus 1, you are going to have r21 multiplied by y1 plus or minus 1 theta phi. And as I told you, this function is known as the spherical harmonic function. one of the spherical harmonics, and this is the radial part of the wave function. This R21 actually we do not have to discuss, because we have already discussed it in the case of 2pz. So, as far as the radial dependence is concerned, this function and the 2pz functions are the same, there is no difference. Okay. So, therefore, I have to look at the just y1 plus or minus 1, you can evaluate it using the formulae that I had given earlier, but what I will do is I have come with a table, so that we can just use the table. So, this here I have a table of all the spherical harmonics that we will ever need, at least in the chemistry lectures, or most of them. So, what we should do is we should look for y1 plus or minus 1. So, if you look here, you get y1 minus 1, the notation is slightly different, because that minus 1 I am writing not on top, but at the bottom, that is all. Okay. So, y1 minus 1 is here, y1 plus 1, where is it? Yeah, there it is. Okay. These are the two functions. What is their form? Y1 plus 1, for example, is actually 3 by 8 pi. We are not terribly interested in this constant, and in fact we can even omit it if you are thinking of just the angular dependence, how it is changing as a function of angle. This is just a constant. Then sin theta e to the power of I phi. Well, if you look at the other function, what will happen is that you are going to have a minus sign, instead of e to the power of plus I phi, you are going to have a minus I phi. So, I can write both of them together, plus or minus. Now, visualizing this kind of function is difficult, because what happens is that this e to the power of plus or minus I phi can be written as cosine of I phi plus or minus I sin phi. Okay, using a theorem from mathematics, we have already discussed this, and therefore, it will contain a real part as well as an imaginary part. So, difficult to visualize, but there is nothing wrong with this function. This is absolutely fine, and if you want to use it, it can be used. So, what we do is we do not make use of this plus or minus e to the power of plus or minus I phi, but instead we make use of functions which are obtained as linear combinations of this e to the power of plus I phi and e to the power of minus I phi. I have told you this earlier. So, the result is either cos phi, or another possibility is you will get sin phi, something that I have already talked about. So, those functions also are shown here. So, if you look here, here is the spherical harmonic obtained by linearly combining these two. This is one possibility. Instead of e to the power of I phi, all that happens is you get a cosine of phi, but then if you have the cosine, you can also have the sine, and that is the next possibility. So, therefore, the way in which I will indicate them is I will say, okay, y1, the magnitude of m for both the functions is actually 1. So, I will write this as y1 1c, yc, because I have put a cosine here, and the other possibility is y11 s, which will be defined to be, well, the normalization factor is a little bit different. You will get a 4 pi here, 3 by 4 pi to the power of half sin theta sin phi. So, these are the functions. These are the angle dependent functions. We simply make use of them because the functions are real, and therefore, easier to visualize. Okay. But then what I should do is I should actually construct polar plots of these two functions. I can do that using Mathematica, it is not difficult at all. But I will make use of a simple argument which should enable you to construct the polar plot yourself. To make that argument, let me also look at y10. Y10 is what? Y10 is actually proportional to cos theta, there will be some multiplicative factor. What is that multiplicative factor? It should be there in the, yeah, well, it is here. Okay. So there is a small mistake here, this 1 should have been down here and 0 should have been up there, but it does not matter, we know what it is. So therefore, square root of 3 by 4 pi into cos theta. This is the function for which we already have made the polar plot, and so we know what exactly how the polar plot is. But then if you remember, Z is equal to r cos theta, right. Remember our conversion from Cartesian coordinates to polar coordinates. Z actually was defined to be equal to r cos theta, x is equal to r sin theta cos phi, y is equal to r sin theta sin phi. This is just to remind you. Fine. Now, if you look at cos theta, suppose I expressed it in terms of Z, you can see that it can be expressed in terms of Z. What is it? It is nothing but Z divided by R. And you see that if you made a polar plot of Z by R, the result actually consists of surfaces of two spheres which are located along the Z axis, right. And with that information, suppose you look at sin theta cos phi, sin theta cos phi actually is x by r. So, suppose you make a polar plot of x by r, what would be the result? The result actually is very simple. It has to consist of two spheres which are located along the x axis, and therefore, what happens is that this function represents what you normally refer to as the px atomic orbital, and this orbital and the previous orbital are different only in that their orientation in space is different. The previous one was oriented along the z axis, while this one is oriented along the x axis, and the same kind of argument will enable you to say that, well, this function is actually y by r, and therefore this is going to be, I mean, the polar plot is going to consist of two spheres located along the y axis. So, you can actually see them using Mathematica. Okay, if you want to have, maybe what I will do is I will plot all of them, px just gone, it has plotted all of them together in one figure. I wanted them to be separate. So, let me try to separate them. That is an interesting figure. No, it does not work. What should I do? It will work now. Okay, this is a px, this one is px, and these two are, as you can see, py and pz. Okay, I mean, previously though I made a mistake, you could see all of them together in one figure. Okay, now we will look at n equal to 3, but before I do that, let me just remind you, in this case we have found 4 atomic orbitals. Remember, n is equal to 2, there are 4 atomic orbitals. N is equal to 1, there is only 1 atomic orbital, and in general for any value of n, what happens is that you have n square atomic orbitals. Okay, for the hydrogen atom, if you give me any value of n, you have n square. That means if I had n equal to 3, I would have 9 atomic orbitals. Okay. So, let us look at n equal to 3. So, if n is 3, I can have L equal to 0, in which case m will be automatically be equal to 0. Let us look at that case first. Wave function psi 310, and as you know, it may be written as R31 of R, y10 of theta phi, and this y10 is a function that we have already encountered. This function is nothing but square root of 3 divided by 4 pi into cos theta, and this is just the same angle dependence that appeared in the case of 2pz atomic orbital, and therefore, we should realize that this is a 3pz atomic orbital that we are going to have, and the angular dependence we have already discussed. So, I am not going to discuss that, but you can look up R31 from tables and write the expression for the total wave function. The total wave function will then look like 1 by 81 into square root of 3 pi into 1 by a0 to the power of 3 by 2 into 6 minus rho e to the power of minus rho by 3 into cos theta. And we shall now make a plot of this R31 against the distance from the nucleus. Let us do that. So, what we are going to do is, you see, we are essentially going to look at this part and make a plot of it against rho or equivalently against R. So, this is my vertical axis. Along the vertical axis, we are going to take R31, and along the horizontal axis, as I said, it can be either rho or equivalently R, because rho is actually given by R divided by a0. Now, because of the existence of rho in my wave function, what will happen is that the wave function starts out to be 0 at the origin, that is at rho equal to 0. Now, you see, this something has happened. I press somewhere. Let me draw this again. Okay, so therefore, the plot actually would look like this. It starts at 0, increases, and eventually when rho is equal to 6, the function, as you can see, will become 0. So, therefore, it turns around at rho equal to 6. This point is rho equal to 6, the wave function becomes 0, or R31 becomes 0, and then beyond that the wave function actually turns out to be negative. So, therefore, and eventually when rho is infinitely large, the wave function will approach 0. So, that is a plot of R31 against rho, and now all the information that we have we will combine together and make a plot which should give you an idea of how the orbital is. So, how will I represent this function? Well, I am going to represent it by shading. Here is the circle, or maybe I can say the sphere with rho equal to 4. This is the sphere, let us say. Then inside the sphere what will happen? The function is actually positive, while outside the sphere the function is negative. On the sphere the function is 0. So, therefore, let me represent this function by shading. You see, suppose I am somewhere here, then I know that the radial part of the wave function is actually positive. So, that is clear from this plot. So, you are somewhere here, the radial part is positive, the angular part also is positive, because I am thinking of positive as a direction. So, therefore, the total wave function which is the product of these two is going to be positive in this region, right. At the origin it has a 0 value, right. Okay, this is a mistake. R31, okay, I did not copy it correctly. If you look at the expression, I am sorry, the expression that is written there is correct. Where is it? R31 is having 4 minus rho into rho, this rho I forgot to copy. So, whatever I have told you by looking at the function is not correct. Okay, I mean what I do is I just look at the function and tell you how it behaves, I do not remember all these things. So, if you that rho actually implies that this plot has to be only slightly modified. Fortunately, it starts with the value 0 there, then increases and then decreases, that is all. Okay. So, therefore, what will happen? Because of that, at the nucleus the function actually has the value 0, and as you go away from the nucleus, what will happen? The function increases. So, the function increases, but on the surface of the sphere the function actually becomes 0, and as you cross the sphere, what will happen to the function? It will change sign. So, you will have a region here where the function becomes negative. But then suppose you are in the downward direction. In the downward direction what will happen? See, the radial part of the wave function is still positive, but the angular part actually is negative in the downward direction. So, therefore, in this region the function will be negative, and then when you cross the sphere what will happen? The function changes sign and you will have a region where the function is positive. And you should also realize, if you say that this is the which axis would you like to say? The y axis, there is the z axis, and you can say the x axis is perpendicular to this. Any point on the xy plane, the function is actually the angular part is cos theta. So, for any point on the xy plane, cos theta has the value 0. So, this is actually a nodal plane. So, how many nodes does this function have? It has 2 nodes, one is this plane xy plane and the other is the surface of this sphere. Okay. There is again, thank you, this is another mistake. So, this is negative. So, this is the orbital that we refer to as 3 P Z. Or maybe more precisely you can put a psi also, which usually people do not write, psi 3 P Z. And then we have to think of m equal to plus or minus 1. I will just modify things here, m equal to plus or minus 1, that means I have to think of y plus or minus 1, I mean instead of 0 I will just put plus or minus 1 here and then plus or minus 1 there, and then what will happen, you will have e to the power of I phi or e to the power of minus I phi, but we are not too happy with that. So, what do? We make use of functions which are real, and eventually what is going to happen is that you are going to get 2 other atomic orbitals which will be 3 p x and psi 3 p y. Their appearance, everything will be the same as this one except for the fact that they are now oriented along the x or the y axis, right, that is all. Then we think of the next situation where n is equal to 3 and L is equal to 2. So, if n is equal to 3 and L is equal to 2, m can actually have what are the values that are possible, let me just list them. M can be 0 or plus or minus 1 or plus or minus 2. These are the 5 different values that are possible. Each one of them will give you a solution of the Schrodinger equation. So, therefore, I have 5 orbitals when L is equal to 2. Okay. So, the first one will have m equal to 0, and what will that be? You are going to have psi, let me just modify things here. Psi 320, it is going to be R 32 into Y 20, right, and Y 20 we can take from the tables, but before I do that maybe I can take R 32 because it is right there on the screen. Here is R 32 1 by A 0 to the power of 3 by 2. Okay, it is difficult for me to see standing there. So, this is the function, and what happens is that we have rho square into e to the power of minus rho by 2, and this actually ensures that if I made a plot of R 32 of R against rho or equivalently R, see what happens is that we have this term R square which actually makes the function vanish at the nucleus. So, the appearance of the plot will look something like that. It reaches a maximum and then it decreases to 0. Now, the angular part of the function, again I will make use of my tables. So, somewhere in the tables I should find y 20, okay, there it is y 20. So, this is the function, and well, the function has this constant. I am not going to worry about that constant. I will just construct, I will imagine that I am going to consider only this part, and I shall make a polar plot of this function. Let me do it very quickly because we know the procedure now. The first thing that I will do is I will make a table of theta and values of 3 cos square theta minus 1. If I put theta equal to 0, I can easily evaluate it. I shall get the answer 2. If I put the answer, if I put 30 degrees, you will get the answer 1.25. 45 degrees, the answer will turn out to be 0.5. 60 degrees, it is minus 0.25. 90 degrees, minus 1, then 120, 135, so this is my small table which is not difficult to calculate, and this you can make use of to construct the polar plots. As I said, I will do it rather quickly. Let me confine myself to the YZ plane. I realize that when theta is equal to 0, the value is actually 2 units. So, I will have to put a point somewhere there such that the distance of the point from the origin is 2 units. Then 30 degrees, the point is 1.25. 45 degrees, the point is at a distance of 0.5. Well, as you go from 45 to 60, you find that the function actually changes sign. So, therefore, there is some point in between where the function will take the value 0. What is that value? You can easily calculate that. It is going to be cos inverse of 1 by root 3. Okay. So, at that value which comes around 53 point some angle, which will be something like this, at that angle the point that you have to put actually coincides with the origin. You can do the same kind of thing on the other side. Okay. And then if you are thinking of the y axis, along the y axis I know the theta is 90 degrees, the function actually is negative, but remember my prescription, when if the function turns out to be negative, then you will forget the negative sign, which means that you are taking the magnitude. So, along the y axis the function actually turns out to be negative, and so we will put a point such that its distance from the origin is equal to 1 unit. I have not accounted for this. This is actually at an angle of 60 degrees. This is 60, let me say, and along that direction you see the value is 0.25. So, point is somewhere here. Same kind of thing you can do in the other direction. So, maybe somewhere here you will have a point, somewhere there you will have a point. You can continue to do that. As I said, this is not a difficult thing, and therefore, let me just join together the points that I have obtained. So, these are directions in which the function is positive. Then we can have these points joined together, and you can continue the plot downwards. using the table. So, this is the appearance that you will get, but to remind you, see in the upward directions the function is positive. Let me remove all these lines that I had put, maybe I will draw it once again. So, the function is positive, in this directions the function is negative, and further you should notice that the function has no theta dependence, and therefore, if I the function has no phi dependence, and therefore, if I wanted to get the 3 dimensional appearance, all that I need to do is take this and rotate it about the z axis, right, and this orbital I will continue discussing this in the next lecture. This is referred to as 3D z square atomic orbital. So, thank you.